Hey everyone, and welcome to this explainer. Today, we've got a really fascinating goal. We are going to look right under the hood of AI chatbots. We're demystifying large language models and, uncovering the sheer magic of how they actually work. And I promise you, we are going to do this entirely without getting bogged down in all that crazy, complex math. Okay, let's dive into this. Just imagine for a second that you stumble across a short movie script. It describes a scene between a person and their AI assistant. Now, the script has all the person's questions, but the AI's dialogue, completely torn off. But suppose you have this magical machine that can read what's left and give you an incredibly accurate prediction of exactly which word should come next. You could actually finish the script, right? You just feed what you have to the machine, see its prediction for that very first word of the AI's answer, and just append it right onto the page. And if we repeat that process over and over, just building up this growing script, you eventually complete the entire dialogue. Believe it or not, when you interact with a chatbot, this simple four-step process is exactly what's happening. It reads the text, predicts the probabilities for the next word, selects one, adds it to the prompt, and repeats the whole shebang. Now, what's really fascinating here is that the machine's core mechanic is completely deterministic, but the output feels so much more natural if we let it occasionally pick slightly less likely words at random. It's kind of like throwing a little wild card in there. That's exactly why a specific prompt usually gives you a freshly worded answer every single time you run it. To truly get how this all works, we're going to treat today's explainer like a blueprint to reverse engineer the machine. First, we'll look at the next word prediction engine, then training in billions of dials. After that, teaching chatbots to be helpful, the magic of transformers, and finally, emergent behavior and black boxes. All right, let's peel back the very first layer of this onion with section 1, the next word prediction engine. This is essentially the basics of autocomplete. Let's actually take a second to formally define what we're talking about here. A large language model, well, actually scratch that. It isn't a thinking brain at all. It's just a highly sophisticated mathematical function that assigns probabilities to all possible next words for any given text. It doesn't just guess one word with absolute certainty. No way! Instead, it mathematically weighs the likelihood of literally every single word in its vocabulary being the next valid step in that sequence. So, how exactly does a model learn to make these incredibly accurate predictions? Let's move to section 2 and see how this builds. We're looking at training and billions of dials, or tuning the machine. Basically, it learns by processing just a downright enormous amount of text, mostly scraped from the open internet. To give you a sense of this staggering scale, and this blew my mind, if a standard human read nonstop, 24 hours a day, 7 days a week, it would take them over 2,600 years to read just the text used to train GPT-3. 2,600 years. And the newer, larger models, they're trained on much, much more than that. So, the large language model, that actually refers to its parameters. You can kind of think of training as tuning hundreds of billions of continuous dials on this massive, massive machine. And here's the kicker. No human sets these deliberately. They begin completely at random, meaning initially the model just spits out absolute gibberish. But by testing itself against trillions of real-world text examples, it constantly compares its prediction to the true next word. Then, this algorithm called backpropagation steps in to automatically tweak all those billions of dials just a tiny microscopic bit, making it slightly more accurate for the next time. The computing power required to actually pull this off is genuinely mind-boggling. To put that into perspective, imagine a computer that could perform 1 billion additions and multiplications every single second. Okay? How long would it take to do the math required to train the largest language models? Well, it wouldn't take a year, not even 10,000 years. At that blazing speed, it would take well over 100 million years. Absolutely wild. Which brings us to step 3 of our blueprint, teaching chatbots to be helpful and moving way beyond just mere autocomplete. Now, what's really interesting about this slide is the clean separation of two totally distinct training phases. Everything we just talked about, absorbing all that internet text, is called pre-training. But, as you can probably guess, the goal of auto-completing some random internet forum is very different from the goal of being a genuinely useful AI assistant. So they undergo a second phase. This is called reinforcement learning with human feedback, or RLHF for short. This is where human workers literally flag unhelpful or problematic predictions, further adjusting those billions of dials to favor the kinds of predictions that you and I actually want to see. Now, we're descending into the absolute deepest architectural core of our blueprint. Section 4, the magic of transformers and processing in parallel. Because really, how on earth do computers crunch all this data? Well, that staggering computation we just discussed is handled by special computer chips called GPUs. They are fantastic at doing many things at once. But here's the thing. Before 2017, language models process text sequentially, just one word at a time, which made them incredibly, painstakingly slow. Then, a team of researchers at Google introduced a real game changer, a model called the transformer. Instead of reading from start to finish, transformers soak all the text in at once, totally in parallel by converting words into these long, complex lists of numbers. What makes transformers truly unique, though, is their reliance on a very special operation known as attention. Alongside feed-forward neural networks, this mechanism allows these lists of numbers, which, remember, represent our words, to essentially talk to one another. They constantly refine their meanings based on the surrounding context, and they do it all simultaneously. And this brilliantly illustrates exactly how that works. Take the word bank. On its own, it's pretty ambiguous, right? Are we talking about a financial institution where you keep your money, or the muddy side of a stream? Well, the attention mechanism looks at the surrounding words in your prompt, and it shifts the encoded numbers for that generic word bank to represent the highly specific concept of a riverbank. The numbers are organically enriched by their context. It's like a giant puzzle constantly solving itself. And that brings us to our final frontier today, Section 5, Emergent Behavior and Black Boxes, where we're going to explore the frankly unexplained fluency of these models. It's easy to just look at the math and the hardware, but what actually comes out the other end is nothing short of fascinating. While researchers design the framework, the transformers, the attention mechanism, the backpropagation, the actual behavior of the chatbot is an emergent phenomenon. It's this specific, uncannily fluent behavior that arises entirely unprompted from the tuning of those hundreds of billions of parameters during training. And because of that massive scale, it makes it incredibly challenging to figure out exactly why the model makes the specific predictions it does. It is, for all intents and purposes, a black box. So the crucial point is really this. We build the machine, right? And we feed it mountains of data to turn all those dials. But if the system is a black box and we don't fully understand the exact mathematical pathways it uses to generate such beautifully fluent text, well, who is really writing the script? It's a profound question, and one that sits right at the very edge of modern technology. Anyway, thanks so much for joining me for this explainer, and remember to keep questioning the magic behind the math.